Hello, my name is Mariah Schrum, and Erin Hedlund-Botti and I will be presenting on our paper, MELD, Personalized Meta-Learning for Robot-Centric Imitation Learning, co-authored by Nina Moorman and Matthew Gombolay. For robots to operate in the real world, they must be capable of learning novel tasks from non-expert humans. However, prior work has shown that humans are suboptimal when providing corrective demonstrations to robots, making it difficult for robots to successfully learn from humans. To overcome this limitation, robots must take into account human suboptimality when learning new tasks. Learning from demonstration can be broken down into two main types, human-centric LFD and robot-centric LFD. In human-centric LFD, the human is in control and demonstrates the task to the robot. An example of human-centric LFD is behavioral cloning, in which the demonstrator provides a series of demonstrations and the agent learns via supervised learning. While human-centric LFD is intuitive to the user, it suffers from covariate shift problems and performs poorly in stochastic environments. Robot-centric LFD attempts to overcome the covariate shift problem. In robot-centric LFD, the robot rolls out a policy, and the human provides corrective feedback while observing the robot. The current state of the art for robot-centric LFD is based upon Dataset Aggregation, or DAgger. In DAgger, the human provides corrective feedback which is aggregated each iteration, and the agent is retrained on the new dataset. While this algorithm works well if the labels provided by the human are high quality, prior work has shown that humans often provide poor labels. To overcome this limitation, we propose to learn to map poor human labels to better labels, thereby improving on the performance of robot-centric LFD. To improve upon the deficiencies in robot-centric LFD, we introduce mutual information-driven meta-learning from demonstration, or MELD. To better learn from suboptimal corrective labels, MELD meta-learns an individual-specific mapping from human labels to predicted optimal labels via long short-term memory, or LSTM-based neural network architecture. We demonstrate our architecture in a driving simulator domain. In this domain, the robot rolls out its current policy, and the human provides corrective feedback that may be suboptimal. Based upon the human feedback, we learn a personalized embedding in d-dimensional space that describes their style of corrective feedback. In this example, we see that this individual is an overcorrector, meaning that they tend to turn the wheel too far when providing corrective feedback. Based on their learned style, we then map their corrective labels to better labels so that the LFD agent can more effectively learn from the human. We employ calibration tasks to learn an individual style of providing corrective feedback. These calibration tasks consist of Wizard of Oz policy rollouts representative of the task space with known optimal labels. We determine the optimal labels via RRT star and model predictive control. For each calibration task, the agent rolls out a Wizard of Oz policy as shown on the right, and the demonstrator provides corrective feedback. We train our MELD architecture on the optimal labels and corrective actions provided during the calibration tasks to learn the personalized embeddings and mappings from suboptimal labels to better labels. Here we show our architecture, which is trained on the calibration tasks. Our network architecture simultaneously learns the style of the demonstrator via personalized embedding W and learns the mapping from demonstrator label A sub T to the difference between the demonstrator label and the ground truth. Our bidirectional LSTM learns the embedding Z, which encodes temporal information about the demonstrator's suboptimality. The subnetwork F sub theta maps this encoding to the difference between the human-provided label and the ground truth. We include the subnetwork G sub phi, which approximates the probability distribution from which W is drawn and is necessary to maximize mutual information. To test the ability of our architecture to learn suboptimal demonstrator styles and improve suboptimal demonstrations, we create a synthetic experiment with synthetic policy rollouts, demonstrators, and corrective demonstrations, which we utilize to train our MELD architecture. In our experiment, we show that similar demonstrators tend to cluster together, suggesting that our architecture is able to learn meaningful embeddings. Additionally, we find that we are able to improve upon the suboptimal corrective labels by 55%.
We next conduct a human subject study using the driving simulator domain, AirSim, and an Xbox steering wheel. Autonomous driving has an intuitive interface for humans and is a common domain used in prior work to evaluate LFD algorithms. The objective in this domain is to teach the car to drive from a start location to the orange ball while avoiding collisions. We recruit 76 calibration participants to complete the calibration tasks and learn the network parameters for MELD. We next freeze the network parameters and conduct a test study in which we compare MELD to DAgger and BC. We recruit 42 participants for the within subject study. Note that our population pool consists mostly of Georgia Tech students. After completing the calibration study and learning MELD's network parameters, we next conduct the test study comparing MELD to baseline LFD algorithms. In our study, participants first provide demographic information and fill out a survey on prior experience with driving and video games. Participants then complete 16 calibration tasks to learn a person's embedding. Note that one of MELD's assumptions is that a person's embedding is static over time. In our study, the calibration tasks are meant to capture the distribution of tasks that may arise when teaching a car to drive from point A to point B. Each participant then teaches the car on a different test task via either MELD, DAgger, or BC and provides 12 demonstrations. After teaching an agent, the participant fills out surveys on workload, likability, perceived intelligence, and trust. All three conditions are experienced by each participant in a random order. To evaluate MELD specifically, we measure percent improvement, which is the amount that MELD improves participant labels compared to ground truth. Additionally, we wanted to determine what metrics impacted a person's style of providing feedback and if they correlated with the learned personalized embeddings. To measure how much a person over or under corrected and if their feedback was delayed or anticipatory, we measured a participant's stylistic tendencies. We used dynamic time warping to temporally match the participant's feedback signal and the ground truth signal. We also collected demographic information such as age and gender and a participant's prior experience with driving and video games. We found that a person's embedding correlated with how much a person over or under corrected, the amount that their feedback was delayed or anticipatory, and their experience with video games. To evaluate MELD compared to DAgger and BC, we measure the objective performance of each algorithm by measuring the distance from the goal at the end of each trial. Additionally, we measure the number of times the agent reaches the goal, the probability of the agent reaching the goal, and how many demonstrations are needed for the agent to reach the goal, or sample efficiency. To evaluate how people experienced MELD compared to DAgger and BC, we measure participants' workload to teach each agent and their ratings of the agent in terms of likability, perceived intelligence, and trust. Here we see the results for the average distance from the goal for each of the agents after each demonstration. We see that MELD achieves a lower average distance from the goal overall. When comparing the last trial, we find that MELD achieves a significantly smaller average distance from the goal compared to DAgger and BC. Next are the results depicting the probability of an agent reaching the goal once over the course of the 12 demonstrations. MELD has a nearly 100% probability of reaching the goal after training is complete, while DAgger and BC are significantly less likely to reach the goal. Here's the probability of an agent reaching the goal twice, 3 times, and 4 times. We see that MELD achieves a nearly 100% probability of reaching the goal 4 times, whereas the other agents achieve less than a 50% chance after training is complete. If a person provides good feedback, then DAgger may be able to learn well. We hypothesized that MELD would outperform DAgger the more that a person is suboptimal. We found that MELD's advantage over DAgger does increase as a person's feedback is further from optimal. Next, we investigate subjective metrics. We find that participants rated MELD as significantly lower workload than DAgger and BC. Additionally, participants rated MELD as significantly higher in terms of likability, intelligence, and trust. To summarize, MELD has the ability to improve corrective labels to be closer to optimal. MELD's learned embeddings correlate with a person's stylistic tendencies and their prior experience with video games. MELD outperformed DAgger and BC in terms of the ability to reach the goal and consistency in reaching the goal. MELD has a greater advantage over DAgger when a person's feedback is more suboptimal. And lastly, MELD was rated as better than DAgger and BC in terms of workload, likability, perceived intelligence, and trust. In the future, we want to demonstrate that MELD can generalize across platforms, so we will evaluate MELD on a robotic arm domain. Additionally, we want to investigate how to map a person's embedding across platforms or domains. Lastly, we plan to learn how to estimate how a person's embedding changes over time and how to provide a person feedback on how to be a better demonstrator. We would like to acknowledge our sponsors, Georgia Tech, the National Science Foundation, Konica Minolta, NASA, and MIT Lincoln Laboratory. Thank you for listening, and we would be happy to answer any questions.